Yeah. Well, thank you both for coming back. This is the last of the new lectures for the course. I didn't move the date over here, but we are July 30th, 2021. So next week we will do review. But before we do that, today we're going to do, I think it's a heat pump problem. But, as we talked about last class, heat pumps and refrigeration cycles are essentially the same thing, right? It's just a different energy benefit. We also talked about how next week we'll run 4 review classes. Thank you very much for volunteering to bring in problems on Tuesday and Wednesday about a Brayton cycle and a turbojet. And then I think on Tuesday, we'll talk about the plans that we have for Thursday and Friday's class. So we've been talking about refrigeration units, right? Sort of, this idea of how do we try to trick the universe, or at least make it look like we're tricking the universe, to move heat from a cold place into a hot place, right? Now, this class, right, we're going to do a heat pump problem. And the only difference, these vapor compression, refrigeration, and heat pump cycles, from a component standpoint, they look exactly the same. They're the same series of components, right? We've got an evaporator on the cold side that's removing heat from the cold place. That boils our fluid so it gets to be a vapor. Then we increase the pressure of the vapor through the compressor. And then we condense that liquid. So we're rejecting heat out into our hot place. And then we have this thing, right? It's almost like a Rankine cycle in reverse, but instead of this turbine, we have a valve here. Remember, the valve, it's isenthalpic. So basically nothing happens here. There's no heat transfer. There's no power. There's just a change in pressure, right? And the difference between a refrigerator and a heat pump is that in a heat pump, the energy benefit is that we're heating up our hot place, right? So it's this heat transfer that happens out of the condenser and into our hot reservoir. Whereas in a refrigeration unit, it would be the heat that we're removing from the cold place going into the evaporator. For both processes, the energy cost, right? Because when we talk about these characterization parameters, it's energy benefit divided by energy cost. Our energy cost in these cases is our net power. And the nice thing is, there's only one component that contributes to net power, and that's the compressor, right? Because this expansion valve, because it's isenthalpic, H in is equal to H out, then m dot times H in minus H out is equal to 0. So it's only the compressor power that matters in the heat pump and refrigeration cycles that we'll talk about in this class. Last class, we kind of drew a TS diagram, right? Again, it looks like a Rankine cycle, except it's going in reverse, right? The difference is, right, so it's going counterclockwise instead of clockwise, right? In a real cycle, probably we're going to scoot this out over here and come up over here somewhere, right? But this is, our constant pressure line. We condensed in our condenser. And then I always exaggerate the line that represents the process for the valve, because I want to make it very clear that it's not a vertical line. Unlike an ideal compressor or an ideal turbine, they're not an isentropic process. It's an isenthalpic process, which means that delta H is equal to 0 and not delta S is equal to 0. Again, the energy cost is the power that goes in. The energy benefit for a refrigerator is this heat that comes into the evaporator, and the energy benefit for a heat pump is this heat that comes out of the condenser. Right? So for this class, when we're talking about heat pumps, it's this heat that matters. Right? So when we're talking about the characterization for heat pumps, again, it's energy benefit divided by energy cost. So in the real case, we can use the first law to get expressions for our Q dot on the hot side and our power, our net power, right? So these are only just two components, right? Because the power is the compressor power, and this is our condenser heat exchange. But I always remember it just Q dot hot because it's going into the hot reservoir. Because then when I come into the Carnot version of the coefficient of performance, right, I know that I replace these ratio of Q dots, right? Because we can turn W dot net into Q dot hot minus Q dot cold if I'm taking the absolute values. But I think about it as Q dot hot and cold because then when I convert it to the temperatures that I'd see in the Carnot coefficient of performance, it's just T hot and T cold. Right now, whenever I'm doing these Carnot calculations, I always use Kelvin and Rankine, right? Even though I could use Celsius or Fahrenheit on the bottom because this is a delta T, this is a temperature that stands alone in the numerator, so I have to use an absolute temperature scale there. So if I didn't know what to do, right, this is funny. I tried to put my elbow on my desk, but I missed it, right? This when I was, it's come back to bite me, I guess. When I was in like grade 11 or something, we had this math teacher. He was a really good guy, but he wasn't like the most coordinated fellow. And oftentimes, students in our class, they take their binders and scoot it out on the desk a little bit. So it was still balanced, right? But there'd be like, 6 or 8 inches sticking off the end. And invariably, this guy would always like put his hand down on the part that was, kind of like half lose his balance there. So it's coming back to me here, right? Right. So, if we're totally lost on one of these problems, right, and we don't know what to do, right, what we got to do is remember that all of these cycles are just a series of processes, right? So we're going to try to solve each one of these processes, right? So we got to say, okay, what's the control volume that's related to the part of the problem that I'm looking at, right? Which part of the cycle is going to give me the answer I'm looking for? Then we can do conservation of mass. So conservation of mass for this cycle, everything is always going to be steady state in thermo 1. And all of the components in my cycle for this refrigeration and heat pump cycles are 1 in, 1 out. So that means that as we chain these things together in series, there's only one mass flow rate, right? So conservation of mass, you might not write it down because it's fairly straightforward here, unlike, say, the Rankine regeneration cycle. Then we do the first law, right? So remember, when we're interested in heat transfer, right, we're probably going to cancel out the W dot term. And when we're interested in the power, we're probably going to cancel out the heat transfer term. We'll probably get equations that we recognize. But then we have this kind of special thing because the valve is isenthalpic. So there's no heat transfer or power. It's just a pressure change. And then we got to ask, what's the fluid, right? Because that's going to allow us to put numbers into our equations so that we can get to numerical answers, right? So we're going to, if you're running out of time, try to get the symbolic equation, because the symbolic solution, I think, doesn't take nearly as much time usually as fixing states. Although today we're going to fix the states graphically. So maybe we'll see that doesn't take as much time as if you have to interpolate all over the charts. All right, so conservation of mass, everything in thermo 1 is at steady state. And, all the components, at least in this cycle, are 1 inlet and 1 outlet, right? We have some assumptions that we can make for different components, right? And then we're going to get equations that hopefully are starting to feel familiar here as we're getting close to the end. Now, we could also get asked, is this condenser process possible or something like that? And in that case, you'd have to do a second law analysis. So then we would write down the second law, and because the system is a series of open components, we would use the open version of the second law, and we'd be trying to find the sign of this sigma dot term, right? That's if it's just asking. So if you get like a multiple choice question on the exam and it says, is this thing possible? You might not actually have to do the math, because maybe you can isolate an equation for sigma dot and find out that all the terms in the equation are positive. And if that's the case, then it's positive, right? But if the problem asks you what's the entropy generation rate, then you'll have to fix the states. Right, so now what's the fluid? We generally have 2 subsets of answers, water or something else with a vapor dome, or ideal gases. Right, so the water, this is more like a water sort of problem, right? Because we're using refrigerants, and because it's this vapor compression and refrigeration loop, right? we've got an evaporator. That means we're taking liquid and boiling it, right? And we've got a condenser, which means we're taking vapor and condensing it. So phase change is something that we have here. So as we draw our TS diagrams, we need to have a vapor dome on there. And then we'll have to ask ourselves, what's the phase of the fluid? Today in class, we're going to fix these states using the pH diagram or the SUVA chart. But you could also do the same thing. You could get the same answers by just going to the refrigerant tables that are in your textbook. It's a bit like Ghostbusters here. You can't cross the streams. We talked about this last class. If you find, say, H1 on the chart and H2 in the textbook, you won't really get a good answer because they use a different 0 point, a different datum, right? It's a little bit, that'd be like adding Celsius temperature to Kelvin. Like it doesn't make sense, right? So you can use just the textbook, or you can use just the table or just the graph here, but you can't kind of mix them together, right? You have to pick one path. For delta S, same thing. We're going to use the handbook or the charts here, but you could also use. There's nothing wrong with using the textbook here, right? And using the textbook would, you'd use the tables just like you would if it was a Rankine cycle. All right, so we talked a little bit about this chart, right? It's just a vapor dome to scale, right? This pH or SUVA diagram. And then we talked about all the funny different lines that are on here and how this graph looks like a bit of a mess when you just look at it, right? It's a bit confusing to look at. If I give you this on an exam, I will give you, because it's not an in-person exam, I would give you, I think, the choice where if you wanted to fix the states using the textbook, I'd be okay with that, because I know sometimes it's hard to get access to a printer or whatever. But then I'll also give you a chart like this, probably that's better resolution than this particular one, and then you can solve your problem that way, like we're going to do in class today.
Quick question. Will we have that chart before the exam begins, or would we have to print it out while...
Yeah, that's a good question. I think that's a good point. I think what I'll do is, I got to still figure out what's on the exam, but I will make one of those charts available to everyone so you could print it out beforehand.
Okay.
And I think I'll do that either way. So maybe after today, I'll do that, and then we can you can just print it out, like if you print out the equation sheet and then you just have it, right? Because I think you're right that, in the heat of the moment, when you only got however much time you have, it's better if you just have it, right? And that's what we do if it was an in-person exam. So I appreciate that's a good point.
All right.
I'll just make myself a note here. Okay, so this is our question, right? So this is from, I guess, 10.35 in at least some version of the textbook, right? So, so here we have this heat pump system, right? We're given some information, right? So here we're told that it's saturated vapor as it goes into the compressor, right? So we ran the evaporator to get to saturated vapor. We're told the heat transfer rate out. We know the temperature at state 2, the temperature at state 3, the temperature at state 4. And we know the pressure at the high side after the compressor. We're asked to find the mass flow rate, the power consumed by the pressure or by the compressor, then the thermal or the isentropic efficiency of the compressor, and then the coefficient of performance of the system. Right? So this would be kind of a good exam problem in that it asks you some different things, and it asks us to use the thermal efficiency, to find the thermal efficiency from the information that we have, which is maybe a little bit different than the way that we've done it in the past. So now I am going to move over here to where I have this same problem here, right? So here we've got a state table, right? So I took the information that we had here and put it into my state table, right? You're obviously, it's not if you're going to be asked cycle problems on the exam, right? It's when you're asked cycle problems on the exam. Um, there will be data on the state tables, right? So it won't be, you won't get a Brayton cycle with 14 states to fix and it's like blank, right? Or you have two pieces of information like you might get in a textbook problem, because you have to legitimately have the opportunity to solve the problem in the time that's available, right? So here, what we did was we took this information down, right? So at state one, we know that the quality is 1 because we have saturated vapor. And we know that the temperature is 0 Fahrenheit, or at least we're assuming, I guess, that this is not a subcooled liquid, right? At state 2, we know the temperature is 180 degrees Fahrenheit, and we were told that the pressure here is 200 psi. At state 2s, so I included 2s over here because it's asking me what the isentropic efficiency of the compressor is, and I can't do that unless I find the ideal exit of the compressor. State 3, we also know is at 200 psi because we're going to assume that the condenser, the heat transfer process, happens at constant pressure. And then I'm told T3 is 110 Fahrenheit. And then T4, we know is 0 degrees Fahrenheit. Again, we're asked to find our mass flow rate, power consumed by the compressor. Oh, hopefully it's not one of those days. And then the efficiency of the compressor and the coefficient of performance. So we're going to start with the mass flow rate. Now, anytime we get a problem that's a mass flow rate question, there's only so many ways we know how to find a mass flow rate, right? So option 1 is we're going to take the area times the velocity divided by the specific volume. Or we could maybe write this as the volumetric flow rate divided by the specific volume. That's one way we can find a mass flow rate. A second way we can find the mass flow rate is look for a given value of Q dot or W dot, and then do the first law. A third way to find the mass flow rate is find a component that has more than one inlet or more than one outlet, and do the first law. So in this problem, we don't know anything about areas or volumetric flow rates. Right? We could find specific volume information. We also don't have any components that have more than one inlet or more than one outlet. But we do have a given value of a heat transfer rate, right? So over here, we know Q dot out is 60,000 BTU per hour. So this means I can do a first law analysis on the condenser. Right, so now I'm going to write down my first law. dE by dt is equal to Q dot minus W dot plus the sum of M dot in H in. Now this is an imperial problem, and even though I'm going to cancel out the kinetic energy terms, Vn squared over 2gc, and the potential energy terms, I'm going to write them down properly. This is a G, not a Q. Minus the sum of M dot out, H out plus V out squared over 2gc plus GZ out over GC. If it's a problem like this and you don't need the kinetic energy or the potential energy terms, I'm not going to dock you for not putting the GC in here, right? But obviously, if it was a turbojet problem that was an imperial, you need to get this correct, right? So here we're going to say it's at steady state. It's passive, right? There's no fan blades in here. One inlet, one outlet, no kinetic energy change, no potential energy change. We're going to get Q dot of the condenser is equal to M dot times H out is H3, minus H in, which is H2. The thing we're trying to find here is m dot, right? So here we're going to have an expression, m dot is equal to Q dot C over H3 minus H2. Now, Q dot C, we know, but we have to think about this, right? So it really gave us the magnitude of Q dot out, right? So this is negative 60,000 BTU per hour. Now, if I wanted to get that to BTU per second, it just depends. Maybe if I was on an exam, I would leave this like this, right? Because it's still some energy per unit time, right? In this, the units here are going to be BTU per pound mass. So what's going to happen is the BTUs will cancel and I'll get pounds mass per hour. They didn't ask me for pounds mass per second. So maybe because it's a test, if this was a test, maybe I don't want to mess with this and screw up the units. So I'm just going to leave it and get a mass flow rate in pounds mass per hour, right? But if the problem explicitly said, find the mass flow rate in pounds mass per second, then I'd have to do some unit conversion here. We have a symbolic solution, but we don't know H2 and we don't know H3, but we do have a mass flow rate equation. And if I could fix the states, I would know the mass flow rate. In the chart, it asks for pounds mass per hour. So even better, we're going to do it right. Thank you. Right? So we don't have to change the units, right? But that's something that you could be asked to demonstrate, but there's potentially better ways to get you to do unit conversion than this, right? Like I could ask you a turbojet problem, right? Where unit conversion is definitely going to be an issue. So now we have a symbolic solution for the mass flow rate. And if we could find H2 and H3, we would have a number, right? So that's good, right? But we do have to be sure, right, that we get the sign right. The thing that would happen if you didn't get the sign right, you'd probably be able to recover from that because you'd get this and you'd find that you had a negative mass flow rate, right? What a negative mass flow rate would kind of suggest is that the mass was going this way, right? Instead of the way it's supposed to be going. So then you probably look at that and say, oh yeah, that probably means I got the sign wrong somewhere. Oh yeah, heat in is positive, but this is heat out, so it should be negative. Next, we're asked to do power for the compressor, right? Now this one, hopefully we feel pretty good about this kind of question. If this one's on the exam, right? If I ask you one like this, I'm hoping that you get it. I'm always hoping that you get the answer right. But this one, at least to get the symbolic solution, hopefully we feel really confident on how we can do this. dE by dt is equal to Q dot minus W dot plus the sum of M dot in, H in plus V in squared over 2GC plus GZ out over GC minus the sum of M dot out, H out plus V out squared over 2GC plus GZ out over GC. Oh, that's GC, not GZ. Although I'm just going to cancel it out anyway because we're going to neglect potential energy changes. We're going to neglect kinetic energy changes. We're going to say one inlet, one outlet. We're going to say that it's adiabatic and that it's steady state. And we'll get this equation that we're hopefully starting to know and love. This is going to be W dot is equal to M dot, which hopefully we found in part A, times H in minus H out, which is H1 minus H2. Now this is the actual compressor power. So that means, you know, the power is what we're trying to find, right, of the real compressor. This is from part A, and we have not fixed our states yet. So we got a symbolic solution. We don't know anything about what's in the answer, but, you know, we've demonstrated our understanding, and if we can solve part A and we can fix state 1 and 2, then we'll be able to get a numerical answer here, right? So we picked the right control volume. Next, it wants us to find the thermal efficiency of the compressor. So again, we're still, or not the thermal, the isentropic efficiency of the compressor. Right? So we're still talking about the compressor, right? And here the compressor efficiency is going to be power over power, right? Probably I just want you to read this equation off of the equation sheet, right? To remember which one. But I can logic this out too, because the compressor power is a cost to the system, right? The ideal compressor is going to consume less power than the real compressor. And I already made assumptions in part B. So now I see that my compressor power, or my compressor efficiency, I'm sorry, ideal on top, so this is going to be m dot, H in is H1, H out is H2S, right? And then this is going to be m dot, the real one on the bottom, 1 minus H2. So, you know, if this was an exam problem, it's kind of like the reason that we asked you part B is kind of a warm-up for this part, because you need the compressor powers. But we already did the first law analysis there, right? So this is going to be H1 minus H2S over H1 minus H2. So the thing I'm trying to find is the compressor efficiency. I don't know any of these terms yet. But again, we're sort of in this place where we're trying to get to in thermo, where if we can fix the states, then we can get a numerical answer. So what's next? Next is the coefficient of performance, right? So COP, right, or gamma, because this is for a heat pump, right? Don't worry if you don't remember the Greek letter. You can just write COP, subscript HP. This is going to be the energy benefit over the energy cost, right? My energy benefit is this guy over here. My energy, and actually, you know, I'm going to write absolute value here. Sometimes it's positive, sometimes it's negative, right? The energy cost is my net power, but my net power is the only power term that matters is the compressor power. But I'm still going to write this out. So here I'm going to say this is Q dot out over W dot net, which is equal to Q dot of the condenser divided by W dot valve plus W dot compressor. But because this is isenthalpic, delta H valve is equal to 0, then that goes away. So this is going to be Q dot condenser over the real power of the compressor. Well, I'll write this out, but so this could be m dot times H out, H3 minus H2, divided by the compressor power, m dot H1 minus H2, right? But this is given. So I'm not going to put this into my calculator again. I think I've said this before, but I'm really great at putting numbers wrong into my calculator. So the fewer numbers I have to put into my calculator on a test, you know, I'm mitigating my risk by doing that, right? Here, then, but if I do that and I just do this BTU per hour, then I also need, this has got to be in also BTU per hour, or sorry, pounds mass per hour, right? I can't mess up my units here. And I don't know H1 and H2 yet. Right? But, you know, I'm looking pretty good, right? I got symbolic solutions for everything. I don't know any of the states, but if I knew all of the states, then I would be able to solve this whole problem, right? Now, the last page here, right, is one of these PV diagrams. And this one is probably the one that I'll send out for 134A. This is in Imperial. Maybe I have a metric version of this one kicking around somewhere too. But the quality of this diagram is much better than the one that was in the lecture. I don't know if you can tell over Zoom, but the resolution here is a lot better, right? Which makes it easier to see all these lines and which ones are dashes and dot dashes and stuff. Now, instead of me trying to draw stuff out here, I think it's probably better for you to see how I've done this on this sheet, right? So now what I'm doing, I'm going to solve this problem. I'm going to fix all the states graphically, right? So here, I sort of embedded the state table on this image, and I have the pH diagram, right? So now I'm going to just go through state by state. So I have 3 of my states are up here at 200 psi, right? So I look at my pressure, right, over here, and it's 200 psi, right? So I take this dotted line here, and again, if you're going to print these things out, I'm a big fan of using colored pencils, so you kind of remember, you know, which lines go with which parameter type, right, or which property. Right, so I know that I have one line at 200 psi. There's really no rhyme or reason. I could have started at state 1, right? But 200 psi is related to 3 of the states, so I did that, right? Now I'm going to start at state 2, which again, you could say that's kind of a weird place to start, right? But the other piece of information I know about state 2 is that the temperature is 180 degrees, right? So I come back here, and I say, oh, 180 degrees, that's over here, right? So I want to isolate this line over here, which I've done in red. And then now I have 2 independent intensive properties, right? And they're each a line on this graph, and they come together at a particular point, right? And that's my state 2. For state 3, I know that the temperature is 100 degrees, right? So here, or 110 degrees, I'm sorry, there is no line for 110 degrees, but here's 100, here's 120, and I can see these lines are fairly evenly spaced. So 110 is probably halfway in between here. So if I draw a line that's pretty much vertical going down, it's going to hit my green line, my 200 psi line, before I get to the vapor dome, right? So that means that my state 3 is over here in the subcooled liquid region. Right, so this is state 3. Now, the other thing that I know is that states 1 and 4 happen at 0 degrees Fahrenheit. So over here, I look over here, and like I said before, if this was like minus 20 degrees Fahrenheit or 20 degrees Fahrenheit, you do always got to be careful, I find, on these graphs, because it's not always clear, you know, what 20 and minus 20, what the difference is. Because they're close together, like, I want to say geographically, but I know it's not like a map, right? But, you know, this negative sign kind of looks like it's also just a continuation of the temperature line. So if you do get a negative thing to add, then you got to put it, you got to make sure you're on the right one, right? Especially as you get close to 0. But we're at 0, we're not negative anything, right? So I'm coming down with this 0 degree line, I hit the vapor dome, and then I go straight across. Right? So I know for state 1 and state 4 that those are both on this 0 degree line, right? And I know something about state 1 explicitly, and I know something implicitly about state 4, right? And the thing that I know about state 4 is going through state 3 and state 4, that's going through one of these valves, right? This is through the expansion valve. The expansion valve is isenthalpic, right? Which means delta H is equal to 0, which means once I know H3, I also know H4. So on one of these pH diagrams, as you go through the valve, it's a vertical line, right? So state 4 is vertically under state 3 because H3 and H4 are the same thing. Now, the thing that I know about state 1 is that its quality is 1, right? So here under the vapor dome, we're still at 0 degrees, right? 0.1, 0.2, 3, 4, 5, 6, 7, 8, 9. So state 1, right, that's this saturated vapor line over here. So that's state 1. Now this is the trickiest part, right? See the zoom, huh? I don't use this very often. Because now you see these two lines here, how they're sloped like this? As we go from state 1 to state 2s, which is the only one we haven't fixed yet, we need to find state 2s. Otherwise, we can't get the isentropic efficiency of the turbine. With what I have now, I can answer all the other parts of the problem. But I don't know what the ideal compressor power is yet. Right? So I have to look, and I think, so these lines, which are, the slopes change a little bit. These are the constant entropy lines. Now, what I try to do is look over here and say, my point is pretty big, right? So there's always some graphical uncertainty here. But I think that point is close to halfway in between these lines, right? But state 2s is going to be up here on my 200 psi line. So I think my state 2s is going to be just about in between these two lines over here, right? So I draw my constant entropy line because we know when we go through the isentropic compressor, entropy stays constant. And then when that hits my 200 psi line, then that's my state 2s. So now I've located all my state points, right? Which is cool because now if I draw vertical lines down everywhere, I'll get values for all of the specific enthalpies, right? Now this next part you can't do if you're doing it yourself on an exam, but I can kind of wipe everything away. So this is another, I think, argument for having different colors, particularly when you're drawing the enthalpies, right? You can just draw vertical lines down, right? So I look at this, right? I'm not at 50. 50 would be halfway between. This is not a log. This is a semi-logged plot, right? So this is linear on the x-axis, but it's a log scale on the vertical axis, right? So, I said, well, it's not 50. Maybe it's like 45, right? A quarter of the way between, 40 and 60, right? Or half the way between 40 and what I think 50 would be. For state 1, I draw a line down. I'm going to say 100. One of the things I don't particularly like about this chart, this is labeled 80, right? This is labeled 60. And I think this is the line that's associated with that. But sometimes it's hard to see exactly where the line is that's associated with this number. But I think H1 is about 100. I think H2 is about 120. And I think that H2S is about 120. And H2, here I said, it looks like it's past 130, but maybe not as far as 135. So I just said 133. Now, I don't care if you get the numbers right? If this is on an exam, you want to kind of do the process right. And this is why, you have the chart. Maybe you're showing me what's going on. I just care that you're doing the process right. So if you pick that's 130 or 138 or whatever, that's okay, right? I'm not grading you on your graphical uncertainty, right? But the good news is now I've got values for all of these variables that I didn't have before, right? So here we already went through the. Right, so here the compressor power, we knew that this was m dot times H1 minus H2. Now we have values for H1 and H2, right? So we can figure that out. Oh, I skipped ahead, sorry. So the first one was the mass flow rate, right? So this was our expression for mass flow rate, right? And here, because we got the sign right on the heat transfer, we get a positive mass flow rate. If I got a negative mass flow rate, that's kind of like a warning sign. It either means my understanding of the direction the mass is going is wrong, or I messed up the sign somewhere, right? So here I got about 682 pounds mass per hour when I put these numbers in. For the power, you could leave this as BTU per hour. And again, on a test, unless it specifically asks you in horsepower, right, then you don't have to convert, right? But, there are conversions on the equation sheet. Plus, it's an open book exam, so I guess you could always Google what the conversion is between BTU per hour and horsepower, right? But here, when I put those numbers in, I get 8.8 horsepower. Efficiency of the compressor, right? So I find, right? So this is why, H2S was a smaller value than H2, right? Because that means that the difference between H1 and H2S is less than the difference between H1 and H2. And here we get a compressor efficiency of about 60%. And then our coefficient of performance, when we put these numbers in, right? And again, because I don't want to fat finger my calculator too much, or if I got bad values for the H's, right? I use the given value of Q dot hot, and then I'm going to divide by the compressive power. Now, both of these things happen to be negative, but even if one of them was positive, I would report a positive value here. So this probably I should have drawn absolute value lines here. So that's how we do heat pumps. We would do refrigeration cycles in the same way. So it's not different, except that the energy benefit is different. We're interested in the heat transfer on the other side of the loop. But the process we would use to solve the problem is the same. Does anybody have questions about this example? Okay, there is another thing that I wanted to talk about instead of taking some time at the beginning of our review period. So this is kind of, we've been talking about these three big questions, right? So I put this together, and this is kind of like what's the key or what's the process for solving cycle analysis problems, right? So if you don't know what you're doing, right, and I think I put this up before, I got this kind of 8-point plan or something, right? It makes me feel like a politician, right? It's like, first we're going to define the characterization parameter, right? Then we can do conservation of mass on all the elements. If it's an internal combustion engine, conservation of mass is easy because nothing happens, right, to the mass. It's just closed, right? Then we do first law on all the components, whether it's an open system or a closed system. You got to pick the right version. If we need to, we'll do the second law. Then we'll fix all the states. It looks nice as just one bullet point, right? But obviously that takes a lot of time, right? And is definitely a way to make mistakes. But then once we've fixed all the states, just like we just did in this problem, then we put those numbers back into our equations, we get numerical answers, right? So then I can find what the thermal efficiency or the coefficient of performance is. And we didn't have to do this in the last problem, but I could then compare that to the ideal or the Carnot efficiency for the cycle, right? But like I said, I'm not great at memorizing 8 different things. So there's really 3 things that I think about when I'm doing cycle analysis problems, right? And like we've said, each different cycle has, different permutations of answers to these problems. So the first question is, how do I characterize the system? This is basically asking, what's the energy benefit and what's the energy cost? Because my characterization parameter is always energy benefit divided by energy cost, right? Even in the case of the turbojet where we don't really talk about efficiency. So I won't ask you that efficiency for a turbojet on the exam. The next question I have to ask myself is, well, in this cycle, I'm doing a lot of processes, chained together. Do I model these processes as open system processes or closed system processes? And the answer to that question will tell me what version of each of these kind of fundamental equations I'll use, right? Or it tells me if I even have to worry about conservation of mass. Because if it's a closed system, nothing happens to the mass. And then, usually the most time-consuming part is kind of what's the fluid? And this is always at least a 2-part question. Because if it's water or refrigerant, then I got to ask myself, well, what's the phase, right? And I also kind of got to ask myself, is it going through an ideal pump? Because I have another different equation for an ideal pump, right? And if it's air or an ideal gas, then I have to ask myself, well, is it constant specific heat or variable specific heat? And then if it's an ideal gas, like I've said, the key to solving these ideal gas cycles is where are the isentropic processes? Because then I've got special equations that I can use, right? So now we can characterize, or we can bin or group together the different cycles based on the answers to these three questions, right? So how do I characterize the cycle, right? What's the energy benefit and what's the energy cost, right? So if I look at most of the cycles we did were heat engines, right? So the energy benefit for most of them, or at least all the ones where I'll ask for a characterization parameter, is net power. We talked about jet propulsion, that these aero engines are a little bit different because we want thrust power, but I'm not going to ask you for thrust power on the exam. Now, for temperature control, here Brayton refrigeration is on this list. You don't have to worry about this. We can run refrigeration cycles with air as the working fluid, but that's beyond the scope of what we talked about in this summer version of the class, right? We actually haven't talked about it for a couple of years in this class. But I left it on here, right? So for temperature control, the energy benefit, if it's refrigeration, it's that we're trying to remove heat from the cold side reservoir, right? And if it's a heat pump, we're trying to add heat to the hot side reservoir, right? So those are the energy benefits. The energy costs for all of my heat engines, the energy cost is we have to put heat in, right? So often we're burning fossil fuels to generate heat. For all the temperature control cycles, the energy cost is that we got to plug them in, right? And we're using plugging them in to run something like a compressor, right? So we're putting mechanical power into the system, right? So that's how we can group these things by the first question. Right now, we have some cycles that are open systems that are going to use, equations like, that have dots on them, right? And if they're closed systems, then we use the equations we used at the beginning. The delta E is equal to Q minus W. This should just be sigma, not sigma dot, or delta S is equal to Q over T plus sigma, right? And sigma works just like sigma dot, where we're interested in is it positive or negative, right? But if it's open, right, then we have these rate versions of these equations. So the only closed systems we dealt with are the internal combustion engines, right? So Otto and diesel cycles. So there we're using the closed versions of the equations, even though for diesel cycles, sometimes we'll get enthalpies in there, right? Specific enthalpies. But that's not because they're open systems. It's just because we had U plus PV. All of the other cycles, it's basically that the different processes happen in different physical locations, right? So the mass is moving throughout the system. So all of the other cycles will use the rate equations with dots in. Then we got to ask ourselves, what's the fluid, right? So if it's water or refrigerant, then we're interested in, what's the phase, right? And we have to draw a vapor dome, right? Because you're going to get asked to draw, PV and TV diagrams. So you should know, or TS diagrams. You should know how to draw those diagrams for all of the different cycles. But if it's a Rankine cycle, or it's a heat pump, or it's a refrigeration loop, you got to draw a vapor dome on your TS diagrams, right? If it's not if it's ideal gas, right? So we do have a fair number of the cycles that work with ideal gases. Then you don't draw a vapor dome on your TS diagrams, right? Right. So if it has a vapor dome, right? If it's a Rankine cycle or a refrigeration loop or a heat pump, then it has a refrigeration loop, right? But if it's ideal gas, which, by number, this is more of our cycles, right? The Otto cycle, the diesel cycle, Brayton, the turbojet engine, and then Brayton refrigeration, which we didn't actually do, right? But that's basically a Brayton cycle in reverse. But don't worry, I won't ask you about it on the exam. Although I absolutely won't ask this. But I bet if you know the process, I bet you could figure out how to do a Brayton cycle. Just like I won't ask you about a dual cycle, which is also in the textbook, right? So that's a combination between an Otto and a diesel cycle. But if I asked you about it and you knew the process, then I think you'd be able to get it, right? So right, so if it's something that bounces across the vapor dome, we got to know, is it a subcooled liquid? Is it a two-phase mixture? Is it a superheated vapor? Right? And we got to know, is it an ideal pump? Because we have a different equation for an ideal pump, right? Specific volume times the change in pressure. And if it's an ideal gas, then we got to say, is it variable specific heat or is it constant specific heat? And then we also have to ask, is it an isentropic process, right? So that's one of the reasons why drawing those TS diagrams is really important, because it'll help you identify where the isentropic processes are. And if you know where the isentropic processes are, then you're going to know when to use those isentropic relationships, right? Which are the like P over P is equal to PR over PR. We use that for open systems, or V over V is equal to VR over VR, which we use for closed systems, or the equations with K in the exponent. Again, one has a pressure ratio and one has a volume ratio. So that's it for today. And it's all the material for this class. So next week, like we said, we will do review problems all week. We'll start with a Brayton cycle, and then I think we'll move into a turbojet problem, and then we'll talk about what to do on Thursday and Friday. All right. Thanks very much, everybody. Have a great weekend.
All right. Have a good weekend.
Thanks, you.